Good morning, everyone. We welcome you to the second day of this 5-day faculty development program. Today, for the first session, we have with us Dr. Jagdish Chand Bansal. Dr. Bansal earned his PhD from IIT Roorkee and is currently serving as an associate
Your
professor in the Department of
voice
Mathematics
is coming
at
less.
South Asian University,
When your
New
voice
Delhi.
is not coming proper, check it.
Before joining South Asian University, New Delhi, he has worked as an assistant professor at ABV Indian Institute of Information Technology and Management Gwalior and BITS Pilani. His research work is focused around form intelligence and nature-inspired algorithms. Dr. Bansal also started Soft Computing Research Society in India 10 years before, and within this umbrella, he has organized many conferences and workshops. So, with this short introduction, we now request Dr. Bansal to deliver his talk. In his
Oh, 1
talk,
minute. Okay.
he
Is
will
it
be
audible to
discussing
the
differential
participants?
equations, their
Upen,
evolution,
just
and
wait.
subsequent implementation.
Yes, sir.
Over to you, sir.
All the participants, is it audible? I am getting less, so I am just asking.
Yes, sir. It is audible.
Okay.
Yes.
Okay.
Yes.
So now I welcome from on the behalf of this FDP to Dr. Jagdish Bansal. Already Upendra has introduced Dr. Jagdish Bansal, and he works on especially particle swarm optimization and differential evolution. So today his talk is on differential evolution, evolutionary algorithm, and progress on that. Apart from that, I would also like to highlight, like currently he is working in the South Asian University, New Delhi, and he had initiated 10 years before this Soft Computing Research Society of India, where he is contributing a lot of conferences and workshops he is organizing every year. Now it's over to you, Dr. Jagdish, to start your talk.
Thank you, Dr. Singh, and thank you very much for this opportunity to speak at IIIT Allahabad. And fortunately, I also worked in one IIITM Gwalior before joining this South Asian University. Thank you very much. Just please confirm whether I'm comfortably audible or not. Anybody just please confirm, because now since I have made my screen full screen,
Anyone
so I can
participant?
Yes, sir. Audible, sir.
Sir, you are audible, sir. Audible.
You are audible.
Okay, fine.
And during this discussion, let me not call this a lecture. Let me call this a discussion. So here in this in this lecture, I'm going to explain the differential evolution from theoretical point of view, from practical point of view, and I will also try to explain the MATLAB code of this, the simple one MATLAB code of differential evolution also. So even if in between you have any question, no need to wait till the end. You can just unmute and can tell me at any particular time, or you can just keep on noting down your questions for the end also. I want to assure you that if I can get your attention for next 1.5 hours, then I promise you that the differential evolution will be crystal clear to you. Means 100% after this lecture, you will be able to understand the research papers on differential evolution. You will be directly jump to the research papers, study of research paper on differential evolution. So I'll start with very simple practical implementation point of view. So let me tell you that this differential evolution is in the category of meta-heuristic algorithms. It is in the, people put this algorithm in the category of nature-inspired algorithm, but let me tell you that this is not nature-inspired, because there is no directly natural phenomena which inspired this algorithm, but it is better we call it mathematics inspired algorithm, right? There is another category, that is mathematics derived algorithms. For example, the simplex method, Newton-Raphson method, Fibonacci search method, golden section search method. All those are mathematically derived methods. And let me call this method as a mathematics inspired method, because here in this method, we are using the differentials of individuals. Please mute yourself, everybody. If Dolly Srivastav, please mute yourself. Dolly Srivastav, please mute yourself. Okay, so here in this algorithm, we are using the differentials of individuals, means x1 minus x2 divided by the time difference, right? You know, differential delta x by delta t. But here what happens, the delta t, the differential denominator, delta t is actually the difference of the, or the minimum unit of the iteration. Delta t is the minimum unit of time, the minimum change in the time. Similarly, here it is a minimum change in the iteration. So iteration counter is always incremented by 1. So delta t will be actually here 1. And therefore, delta x, the differential becomes delta x by delta t, so it becomes actually delta x only, right? So delta x means x2 minus x1, x3 minus x2, and so on, right? So the differential, the difference of two vectors can be told as a differential, right? Differential. So difference of two vectors is actually the differential right here. And all these update equations in this algorithm is based on the differentials, and therefore this algorithm is called the differential evolution. Why it is called evolution, let me tell you that word also. Basically, the population based algorithms, where you are solving a problem using a population of solutions. You are taking so many random solutions and then you are updating them based on some nature inspired phenomena or some other way, right? You are updating that. So basically the population based optimization algorithm broadly can be classified into two parts: evolutionary algorithm and swarm intelligence based algorithms. However, from last 10 years, there is a trend that there is no sharp boundary on the evolutionary and the swarm intelligence based algorithms. There are the algorithms which has both the properties of evolutionary algorithm and the swarm intelligence based algorithms also. So this algorithm has evolutionary operators. Many of you must have heard about the genetic algorithm, right? So genetic algorithm is an evolutionary algorithm. It's a purely evolutionary algorithm because it has crossover selection operator, crossover operator, mutation operator. So these are the selection, crossover, and mutation are the evolutionary operators. The same operators are also being used in differential evolution, and therefore it is an evolutionary algorithm also. But there is a change. This algorithm is not purely an evolutionary algorithm also, because in evolutionary algorithm always the crossover comes first and then the mutation. But in this algorithm, the mutation comes first and then the crossover. What I mean? After having the crossover, the population is mutated. Crossover means two parents meet and they produce two offsprings, two children, right? And then these two children's, or the two parents, whatever is the, after selection or after, even after, just after crossover also, the children's mutate. So the mutation comes after the crossover, means the children's mutate. Here in the evolutionary algorithms, children's mutate. The next generation take part in the mutation. But in the differential evolution, mutated population takes part in generating the new population. That's the difference. The mutation comes first and then the crossover. So the mutated population is responsible for generating the new population. That is the major difference in evolutionary algorithm and the differential evolution. But since it is using the differential evolutionary operator, selection, crossover, and mutation, and therefore this is an evolutionary algorithm also. And since here in this algorithm update is based on the differentials of the vectors, right? Differential, I already mentioned, the differential is equivalent to the difference of vectors, because the minimum increment in the time is the minimum increment in the iteration, and therefore delta t becomes 1, right? And so differential means difference, right? So differential evolution, the name is differential evolution. This is a population-based algorithm, means here in this algorithm also we will take a population of solutions and then update it gradually to make it an optimal solution. This is the, you can see here on the bottom, this is the basic paper in which this algorithm was first time published. It was actually introduced by Stone and Price in 1995, but the first publication came in 1997 using this paper. So this is the basic framework of this algorithm. First of all, initialization of the vectors, initialization of the solutions, right? Population of solutions, and then the mutation with differential operators. Mutation, what I said is it uses the differential. So these differentials are used in mutation. Mutation here is a different kind of operator, which is based on the please mute yourself, Shiv Ranjan. KP sir, can we somehow mute everybody else? Means can we do some
Yes,
settings so that
we can do that now. Yes, now it has been done.
I think mistakenly people, accidentally they are switching on their mics.
So all the participants right now, I am muting all. If you have a question right now, write in the chat
Yes.
box. And later on, if discussion held, I will allow everyone to unmute. So to
Okay.
lecture should go without any disturbance. I am muting all.
Otherwise we can do just they can mute for the question only. So meanwhile,
Okay, once they will write in the chat, I will unmute them.
Yes, that will be perfect.
Yes.
That will be perfect. Yes.
Okay.
So please mute everybody. I think I will also be muted. Am I audible now?
You are audible. You are audible.
Okay. So the differential evolution, I already mentioned that the difference between the differential evolution and the other evolutionary algorithm, that you cannot say absolutely it is not an evolutionary algorithm, because here the mutated population takes part in the crossover, and in evolutionary algorithm the children take part in the crossover, in the mutation. Okay, so the major advantage the differential evolution takes is because of the distance between the two individuals, because I told you that the difference in the two vectors is the major region for the mutation, is the major region for the updation, and this difference will be less or will be higher. It will completely depends upon the distances between the individuals in the search space, that how far they are lying currently, right? So distance is very important measure to calculate the diversity in the population. If distance is too high, then these differences make sure that the population takes large step sizes, because you are taking x1 minus x2. So if x1 and x2 are too far, then the step size in the mutation will be higher. And if the distance between the individuals is less, then the step size will be small. So it is, adaptive according to the requirement. If the distance is high, then the step size is high. If the distance is less, then the step size is less. So taking the difference of vectors in the mutation step size has an advantage, that according to the requirement, the population is taking step sizes, or population is moving. So here I already mentioned that distances are good measure or good indication of the diversity of the current population. If there are large distances between individuals, it tends to region that individuals should take large step sizes in order to explore as much as possible. Similarly, if the distance is less, then they should take small step sizes to exploit that area. So, in all these meta-heuristic algorithms, there is a very famous word, exploration and exploitation. So this particular algorithm takes care of both exploration and exploitation according to the requirement, because if the distance is very large, exploration is happening, and if the distance is less, the exploitation is happening, right? So this algorithm is actually popular for having good exploration and exploitation balance. Simultaneously, this algorithm is also popular because of its simplicity, because of its ease of implementation, and because of its speed. The most important, its speed. This is very fast algorithm as compared to other continuous optimization algorithm. Let me tell you, particle swarm optimization, spider monkey optimization, artificial bee colony algorithm, all these are the continuous optimization algorithm. Out of all these algorithms, this one is the most fast algorithm. This is the fastest algorithm. So this is very popular because of all these reasons. Okay. I already mentioned that this is the behavior. Because of these differences, we can get the exploration and exploitation both simultaneously according to the requirement. And the first step of mutation is therefore to first calculate one or more difference vectors, x1 minus x2 or x2 minus x3 or x1 minus x3, whatever. So one or more difference vectors are calculated in the mutation. Okay. Let me come here. This is the this is the mutation operator. I already told you that the major two operators are there in the differential evolution. Of course, third operator is by default selection operator. I'll tell you one by one all these three operators. So the first operator is the mutation, second is the crossover, third is the selection. Let me tell you, be able to explain you the first two operators, you are done with the 95% of the differential evolution. So now I request all to attend, be more attentive for these two operators, the mutation operator and the crossover operator. So this is the basic building block of the mutation operator. This is the basic equation for the mutation operator. The objective of mutation operator is to generate a trial vector. Let me tell you what happens. Just imagine this kind of situation that you have a father, you have a man, to generate the offsprings, to have the children's, you need a woman, right? Man and woman, or parents required, mother and father are required. So suppose a father is there, so you want to create a mother, because in evolutionary algorithm you select mother and father from the population. But here in this algorithm you have only a father, you need to create the mother, right? And this trial vector is nothing but a mother. So actually the objective of mutation is to create a partner for this father, so that the population can be generated, so that this mother and this father can generate the population in the next operator, which is the crossover operator. Objective of this operator is to generate a trial vector. Let me tell you, generate a trial vector, and this trial vector or this mother is generated for all fathers. All fathers means all the population, all the vectors, all the potential solutions, every member of the population. Let me call that parent vector. Let me call that each vector. Suppose I have a population of x1, x2, x3, xn. So please bear with me. I don't have anything here to write. I'm traveling. Actually, I'm not at home. Otherwise, I would have written on my screen. So I'm here only with one laptop. Just imagine the situation. I'm explaining therefore slowly. You have the solutions x1, x2, xn and population. So for x1, you will generate a u1. U1 is its partner. This is one parent, x1 is the one parent, and you will generate one u1. So this u1 and x1 will do the crossover and will generate one offspring. In evolutionary algorithm or in genetic algorithm, you must have heard, if you have studied the genetic algorithm, two parents generate two offsprings. But here, since you are taking only one parent, this trial vector is generated from the population itself. So you are generating only one children, right? In genetic algorithm, you are generating two offsprings. Here you are generating only one offspring. or one one child, sorry. So you have one x1, you are generating one u1 for that, so mother, and this mother is called a trial vector. Just please remember these words: parent vector, original vector, right, x1, and the trial vector, the mother, the u1. And this u1 is generated using a target vector. Now what happens? The mother cannot be generated with the help of the parent. Otherwise, the father properties will be there in the mother, and therefore no much improvement you can expect in the children. In the child, you cannot expect much improvement, and therefore the parent, for a father, the mother is generated based on some other vector, and that other vector is called the target vector. I hope you got my point, that why this target vector is selected different from the parent vector, different from the father, so that the new features, new genes can come, new chromosomes, new genes, sorry, or new properties, new features can be included in the child. Parents genes will definitely come, but some new genes can come, so that the mother is generated based on a different vector. Means the wife, husband wife, so wife is always from some other parents. Sister and brother don't marry, because it is expected that the because of this reason, that the mother should have the different genes, so that the child can become better. So it can have both good genes, right? So the target vector is selected different from the parent vector. Here is the major difference of this algorithm with other algorithms in this category, population based category. Like in artificial bee colony algorithm, if you have heard, then the similar kind of equation is there. The new solution equal to old solution, means the new solution is generated based on the old solution, means it is carrying the old properties, because the crossover operator is not there in those algorithms. That's why they are carrying the properties of the old solution. But here we are going to do the crossover operator also, and therefore we are generating the mother based on some other parent, and that other parent is called the target vector. So now I hope you remember now these three words: parent vector, the original vector; the trial vector, the mother, which we are going to generate using the mutation operator; the target vector, the randomly selected solution from the population other than the parent vector, other than the father. So this target vector is different from the father, or different from the parent vector. So your mother means the trial vector equal to the target vector. This is the equation. If we can understand this equation, I think this is the only thing which is different, which is new in this algorithm, different from other algorithms. So the trial vector equal to the target vector plus this scale factor is a coefficient, a scale factor. This is usually denoted by f. Mathematical equation I'm going to write in the next slide. So this is scale factor f. This is a user parameter. This just to give the weight, that how much difference, how much weight to be given to this term, This term is the difference of the two vectors, and these two vectors, the first vector and the second vector. Look at my cursor. The first vector and the second vector. This is the difference of these two vectors, x2 minus x3, and these two vectors are selected randomly. Let me tell you, they are not serially, they are selected also randomly. So the target vector is selected randomly, and these two vectors are also selected randomly, right? They are influenced from these two vectors. Differential, you may call this is the differential. And why I'm not in the differential, why I'm not dividing by delta t? This is the difference of the two vectors, x1 minus x2. Why I'm not dividing? The difference is t1 minus t2. Why I'm not writing t1 minus t2? Because this is the difference in the iteration, right? Minimum unit of the iteration, and that is 1, and dividing 1 is the same thing, right? So differential becomes the difference here, right? Both are equivalent here in these algorithms, because here the time is not the time, but time is the iteration. So what I said is the target vector, trial vector equal to the target vector plus a scale factor multiplied by randomly selected two vectors. Here it is must to note that all these vectors, target vector, parent vector, and these two randomly selected member. So these four vectors must be different. All these four are different. So now I hope you can understand that in order to implement the differential evolution, your population size should be minimum 4. This is very famous question, that the minimum population size in the differential evolution is 4. Minimum population size in differential evolution is 4. This is the reason, right? So let me explain you based on the selection of these target vector, that this target vector, some people, Stone and Price said that some people may use this strategy, some may use different strategy. So initially he proposed 5 different strategies for the selection of for this mutation equation. This is the mutation operator. That's all. This is the mutation operator. So for this mutation operator, initially the Stone and Price proposed 5 different strategies based on the selection of the target vector, that how this target vector is selected. It is selected randomly, or it should be the best, or it should be what, right? So based on the selection of the target vector and the number of differences. I hope if you remember earlier I said the mutation is based on the differences of vectors. So these differences, maybe this term may be 1 term, or maybe 2 term also, maybe 3 term also, maybe n number of terms also. So, right? So instead of having only one difference vector, you may take other difference vector, number of difference vectors also. So based on these two things, target vector, selection of the target vector, and the number of differentials and the selection of the target vector, Stone and Price proposed 5 different strategies, 5 different mutation operators, 5 different formulae for the difference mutation operator. And these are the 5 different formulae for the difference mutation operator. Let me explain you one by one. These strategies are denoted like this: DE rand 1. What does it mean? I'm just coming on that. The trial vector equal to here is the target vector. This is the target vector, and this target vector is selected randomly. Here I use this word, this DE for the differential evolution. This rand is for if the target vector is selected randomly, plus this f is the scale factor whose value is suggested by Stone Price to be 0.5, but it should be anything from 0 to infinite, but it is good to have it between 0 and 1. Why it should be between 0 and 1 only? Why the Stone and Price? Theoretically it can be anything, any positive number, but practically why I'm suggesting that it should be between 0 and 1, I'll let you know just during the numerical example explanation. I'll let you know that. So the trial vector equal to target vector selected randomly. So here is the random, and this is only one term of the difference vectors. This is one randomly selected vector, this is another randomly selected solution. So this is the difference of vector. So difference of solutions, or difference of vectors, or difference of the randomly selected potential solutions, current population members. This is only one term, and therefore here it is 1. So DE rand 1. Therefore I will write it DE rand 1. Now instead of this randomly selected member, if you are going to write here the best solution, means what is the target? Why this best is also working? Because every father may think that I got the best wife, right? Means whose genes are the best, I always tell a story. George Bernard Shaw and a heroine from the Hollywood. I don't know. I don't remember. There is a story. I don't remember the name of the heroine, but I heard this story that George Bernard Shaw was a very intelligent man and very wise man, but he was very ugly. Means his face is not good. means he was very, very ugly, and the heroine was stupid, means not very intelligent, but very beautiful. So she went to the George Bernard Shaw and said that let's marry so that we will have the children who are intelligent like you, wise like you, and beautiful like me. Then the George Bernard Shaw was intelligent. So everybody wants, the best, the best partner, so that the children will be the best, right? But of course, if you are best only, then you can expect the best children. Otherwise, the George Bernard Shaw immediately declined that no, no, no. There is equal chance, 50% probability that they are wise like you and beautiful like me. So this is not a good idea. So actually the partners should be the best, right? So to generate this mother, let the father of this mother should be the best one, so that this mother can have the best genes, right? So best solution of the population is selected. So this also makes sense, right? And this also makes sense just to have the different genes, right? For the better exploration. But in this case, the convergence speed of the algorithm will be very high, but the exploration will be less, right? So if your search space is such that you may think that your problem is multimodal, then this second strategy is not for you. But if you know that your problem is unimodal, it's a single model, then this second strategy is good for you. And if it is a multimodal, then this first strategy is for you. So, if you want high convergence speed and you know that there is only one solution there, so let's get inspired from the best only, right? So this strategy is also proposed, and this is the one difference. So here is the one, and here is the best. The third strategy, that instead of one difference vector, there are two difference vectors. So this is 2. Now, here, this third strategy is the target to best. This target vector is nothing but the parent vector, like in artificial bee colony algorithm, or like in particle swarm optimization, right? Like in spider monkey optimization, like in gray wolf optimizer, where the new solution is inspired from the previous solution. So the mother is getting the genes from the father, right? So here this trial vector is generated with the help of the parent vector. But here there is a difference, that the other things are taken care here, that this term has 2 random vectors, and here this is inspired by the best solution also. So this strategy is known as the target to best. Another is that you are keeping here the best, this strategy, and keeping, instead of one term, you are keeping 2 terms. So there are 2 terms here. And another strategy is that here you are taking the random and taking 2 terms, right? Let me tell you that Stone and Price suggested these 5 strategies, but now the differential evolution is not limited to these 5 strategies. Now thousands of these strategies are there in the differential evolution. So instead of these 2 difference vectors, 2 terms for the difference vector, you can take more than 2 also. You can take all possible difference vectors here, but of course the algorithm will be slow then. So you can make some customization according to your problem. Now what happens? This is the mutation operator that I did. Of course, I'm going to implement also this operator. Next operator is the crossover operator. So based on this, I'm coming to the crossover operator. Initially, Stone and Price suggested 2 crossover operators, exponential and the binomial. So based on these exponential or binomial crossover, he proposed now total 10 strategies. 5 strategies for mutation plus exponential, so total 5. Now 5 mutation plus binomial, so total 5. So total 10 strategies overall, means every mutation strategies with different crossover operators, exponential and binomial. He proposed total 10 strategies. So now finally you have this strategy: DE best 1 exponential, DE rand 1 exponential, DE target to best 1 exponential. Similarly, after exponential, these are the binomial. So bin for binomial, EXP for exponential crossover. So the last term here is for the operator. sorry, crossover operator. Now, what is this? How this crossover operator is working? Let me explain you. Here is the crossover operator. This, if I will be able to explain you this formula, I'm done with my job. Look here carefully. I think I have selected the wrong slide. Just a second, huh? Just a second. Oh. Can you give me just 1 minute? I think from here I have a better slide. I made better slide now. So let me just open a different slide from this slide. Just a second. Give me a minute only. Actually, there may be some, some folder confusion. So no problem. I'll continue with this. No problem. Let me explain you. The change of the laptop. Sometimes it happens. So the crossover, this is the major formula. You just see at this formula, my cursor. If I will be able to explain you this formula, I hope I have done with the crossover operator. So give me the attention for this formula. You have now, I told you that in mutation operator, you have generated a mother, that is called the trial vector u, that is this u, right? And you have a parent, you have a father, parent, and you have a trial vector. So father and the mother, these are the two things. Now the child, let me call this x dash. The child is x dash. This is the father, sorry, this is the father and this is the mother. X is the father, U is the mother. Now this child will have the genes either from the father or from the mother. Now which genes will come from the father and which genes will come from the mother, is this decision is to be taken in the crossover operator, right? So in the crossover operator, we are going to generate a child, and this child is going to take some genes from the father and some genes from the mother, right? And you know that father is the parent vector X and the mother is the trial vector U, which is generated from the in the mutation operator. Now this child is taking this gene, jth gene. Jth gene means, there is some solution. How the solution is represented? X1 comma, if it is a two-dimensional solution, then it is x1 comma x2, right? So this x1 is the first dimension, x2 is the second dimension. So this jth solution or jth dimension, jth gene, is selected from the mother if this J belongs to this capital J. Now this capital J set, this set is called the set of crossover points. This capital J is known as the set of crossover points. Look here at the cursor, set of crossover points. Now how this set of crossover points is created, it differs crossover operators to crossover. If it is binomial, the strategy is different. If it is exponential, it is different. How this set of crossover points is made, I'm going to explain you in the next slide. Let me just explain you the crossover operator, right? So this crossover operator will take the jth gene from the mother if it belongs to this set of crossover points. Otherwise it will take from the parent. That's the simple crossover points. Means you have two options. Your gene will come either from the father or from the mother. So you will take it from the mother if that particular gene number is in a particular set, and this set, this list of genes, if it is this gene number 1, if it is in the list, okay, you take it from the mother. Then if not, take it from the father. That's this crossover operator. Simple, right? Now how this capital J is made, let me explain you for the binomial crossover. Right, for one crossover I'm explaining you, and for other I will share these slides with you so you can have. Let me explain you for the binomial crossover. First of all, let me consider I'm explaining here in this slide, I'm explaining the construction of the capital J, construction of this set of crossover points, right? So let me explain you, let me consider that the total solutions are nx, means the population size is nx number of solutions are there in the population. So u1nx means the uniform random number from this set 1 to nx. Means suppose 50 is the population size, so 1 to 50, select any integer from 1 to 50. Let me call this j asterisk, and this j asterisk, this first randomly selected gene, let me call this gene. So this first randomly selected index, sorry, let me call it index, will be by default in the set of crossover points, will be by default, right? So you will take this j start, you will start this j with j asterisk, right? Initially this j is 5, the null set, and then you will take this j randomly selected member in this, right? Why I'm taking this randomly selected, why I'm not finding this j asterisk based on certain rules? Because you want at least one gene, at least one feature from the mother, because whatever the points will be here in this set, they will come from the mother. So at least one. If I will not take this, then whatever the rule I'm going to explain you for the binomial crossover, it may be that no gene is selected from the mother, and then your child will be the copy of the parent, of the father, and it means no change in the new solution. Old solution and a new solution will remain same. You want the change in the new solution, so you need at least one gene from the mother so that your new solution is modified. Otherwise it will be a copy of the parent, of the father, and therefore you have selected one randomly selected index from this these solutions. So j asterisk, right, 1 to nx. Oh, sorry. I think I mistakenly I told you this nx is not the population size. Now I remember I told the population. Nx is the dimension of the solution. If it is 2-dimensional problem, 3-dimensional problem, so nx is that 3 or 2 or 4 or 5, right? So nx is the dimension of the problem. So how many genes are there? How many genes are there? That is selected randomly from the for the mother. Now, other crossover points will be there in this set or not will be decided based on this rule. Let me explain you this rule, this cursor. First of all, for each dimension, I will check a random number between 0 and 1 if it is less than a probability PR, and this probability PR is known as the crossover probability. If you remember, in the mutation operator there was one user defined parameter f. In the crossover operator also there is one user defined parameter, that is the probability of crossover, and this probability of crossover PR is determined by the user, and usually it is again like in genetic algorithm around 0.7. It is again around 0.7 like in genetic algorithm. It should be higher, means you are giving more opportunity to the mother to influence the parent, the child, right? So here is the crossover probability. So you will generate a random number between 0 and 1. And if it is less than this crossover probability and that particular J is not already included, because J asterisk is already there, is not already included in the capital J, then you include this J in this J, in this capital J. Means if for any J, small j, the random number between 0 and 1 is less than the crossover probability, then that particular J will be included in the set of crossover points. And this is the way how we create, how we generate, how we will construct the set of crossover points. I hope I have explained you the crossover operator. This is for binomial. You can similarly, you can define your own rule also. You can define your own crossover operator also. People have defined so many modifications are there in the differential evolution where people have defined different crossover operators. So what they did, they defined different rule of selection of this J in the set of crossover points. Binomial, this is the rule. In exponential, another is the rule. Similarly, you can define your own also, and then you can write your own research paper also on this, means your own crossover operator also. But make sure it should be different from already existing, because hundreds of the crossover operator people have defined for genetic algorithm and for the differential evolution. Okay. This is the exponential crossover. So just I'm skipping because of the time limitation, so that I can explain you the numerical example and the MATLAB code also. Because what I understand that if numerical example is the best way to explain the things, these algorithms in crystal clear way. So I have explained you the mutation operator. Let me just recap these. In the mutation operator, you generate a trial vector for each parent vector, and this trial vector and the parent vector do the crossover and generate a child in the crossover operator. Now, what happens? You have a parent and you have a child. You know, the population on the earth is constant. By and large, the population on the earth is constant. धरती पे जितनी आत्माएं सब फिक्स हैं. अगर इंसान मरता है तो एक गधा पैदा होता है, गधा मरता है तो एक इंसान पैदा होता है. It is said, it's a general philosophy of the mythology, कि total souls on the earth are fixed. Similarly, the total population, total number of individuals in the population, in the algorithm are always fixed. Now you have a parent and you have a child. So if the child is there, then child and the father, parent and the child both cannot survive. Either parent will die out or the child will die out. Whoever is the better will survive. And this is called the selection. Now who will survive? Let's select them. One of the either the parent or the child will survive, and the selection of who will survive, the selection of this is called the selection operator. And usually in differential evolution, it is called the greedy selection. It is called the greedy selection. Greedy selection is just, it's a fancy name. It's a very simple. If your child's fitness is better, child will survive. If your parent's fitness is better, parent will survive. That's all. Simple. Nothing. No mathematical formula or not much mathematics here, right? So you have the three operators: mutation, crossover, and selection. Selection means whichever is better will be the part of the population, and the weaker will die out. That's the evolution, right? This is the complete DE algorithm. So there is nothing special in the complete DE algorithm. You have the control. That's why I was searching the new slide. Here it is denoted by beta. Actually, in my lecture, I denoted it by F. So this was the change. Okay, no problem. So this is your F, right? Actually, instead of beta, this is F. F is the scale parameter and the probability of crossover. Only two parameters. Only two parameters are there: probability of crossover and the scaling parameter. These are the two parameters which are to be fixed first of all, and then you generate a random population of ns individuals. This is the population size, and then you, for each individual, you find the fitness. Of course, you have to calculate the fitness so that you can determine when to stop the algorithm, evaluate the fitness, determine the stopping criteria, whether to stop the algorithm or not, and then apply the mutation operator to generate the trial vector, and then apply the crossover operator to generate the child, and then do the selection. Here is the selection. This is the selection operator, that if f of x dash it means the fitness of this child is better than the fitness of parent, then child will included in the population, otherwise the parent will be included in the population. Simple. And then whatever up to the stopping criteria is after this, whatever is the best solution you obtained, report that solution. That will be your solution. Now I'm coming to the numerical example of this algorithm, but let me tell you that this is the algorithm which is very popular for the continuous optimization problems. For discrete optimization problems, it's not that popular. I may not recommend you this algorithm for the discrete optimization problem, but for continuous optimization problems, it is a strongly recommended algorithm and very simple. You just see that in just around 45 minutes, I have explained you this algorithm. Only three operators: mutation, crossover, and selection, right? And those three operators are also very easy to code also. In 15-20 minutes, you can write code in whichever language of this algorithm. Here I have explained you about the control parameters, that usually the population size. What should be the population size here? So population size is usually recommended as the 10 times of the dimension of the problem, number of the decision variables in the problem. Suppose you have a three-dimensional problem, three decision variables are there in your optimization problem, then it is recommended that you take the population size 30. You have 550. Of course, if you have 500, suppose, then 5,000 population size is not recommended. Otherwise, your algorithm will be too slow. So, around 50 is the 30 minimum, but 50 is the most recommended, most optimal, or most famous, most usual population size. But my practical experience says that you should not exceed the population size more than 200, right? More than 200, if you will exceed the population size, your algorithm may behave differently, right? So it is not recommended that you increase the population size by more than 200. Another thing, this I already explained, that the minimum population size is greater than 2nv plus 1. So nv is the number of differential vectors. So if you have one term, then it should be greater than 2 into 1 plus 1, means ns should be greater than 3. I already told you that the minimum population size should be 4, means greater than 3. And if you have more difference vectors, accordingly your population size should be decided. Okay, so let me now come to the DE. So numerical example. Let me come to the numerical example of this algorithm. I will explain you this algorithm using this numerical example. Is it visible, my PDF? Is this PDF visible? Can anybody please confirm? KP sir, can you please confirm?
Yes, sir. It's visible.
Yes.
Sir, it's visible, sir.
Okay, thank you so much. So you have this. Let me explain you this example in 4 parts. The problem definition. First of all, you take a population. This is the problem which I have taken. Just this is end calculation I'm going to demonstrate. So I took only 2 variable problem, x1 square plus x2 square. This problem is known as the sphere problem, and this is a minimization problem. The search space is -5 to 5. I hope you understand that the minimum solution is 0, the optimal solution is 0, 0, and the optimal value is 0. So this we are going to now obtain from the differential evolution. Why I'm explaining you in this way? Because I'm going to code also in this 4 parts, right? So problem definition, you define first of all the problem, and then the differential evolution operators, oh sorry, problem parameters. So first of all, the population size. So I took it 5, right? Just for the demonstration purpose, but practically it is not recommended. Your population size should be minimum around 30. Dimension of the problem, here it is 2. I told you that this is nx that I was talking, right? So it is 2 here. The stopping criteria, I took 2 iterations. It depends upon your requirement of the accuracy. A scaling parameter is 0.5. It can be any positive number, but I took it 0.5. It is suggested by the Stone and Price, the original developers. Why I took it 0.5? Why I recommend it to be less than 1? I'll tell you when I'll take the mutation operator, the numerical example. Crossover probability is, as per the suggestion, 0.7. The third step is the initialization of the population.
Excuse me, sir.
Third step, yes.
Sir, sorry to
Yes.
disturb in between, sir. I want to know about population size. Means what is population size and how we should select? मतलब कितना होना चाहिए, sir? It should be if
So
we work on any domain.
I think you missed this. I all just
Starting.
Here. If you remember, I just suggested this. This should be the population size. It is recommended. Empirical studies, the numerical studies suggested that the population size should be the 10 times of the number of decision variables. Like in this example, the number of variables are 2. So according to this study, the population size should be 20, 10 into 2, right? It should be 20. And the minimum population size for anything, this should be 2nv plus 1, right? It should be minimum 4. And that's why you see that even it is, I'm doing, I cannot take 20 because, I'm going to explain you through hand calculation. So practically it is not recommended to take 5, but just for explanation purpose, I took 5. So here it should be 20, but I took 5 because 4 is the minimum. Otherwise, I will not be able to implement this algorithm.
Thank you so
Right?
much, sir. Thanks.
So initialization, this is the third step. You initialize the population. Initialize the population means you generate 5 vectors, 5 solutions randomly in the range -5 to 5. So here, this is the one solution. It's a 2 variable problem. It's a 2 variable problem. So you are generating an ordered pair like this. This is a random number in the range -5 to 5. This is also a random number. This is also a random number in the range -5 to 5. This is also a random number in the range -5 to 5. So all these are the random numbers in the range -5 to 5 and we generate 5 solutions and calculate the fitness. If you remember in the algorithm, after generating the population, you were calculating the fitness. This fitness is calculated. Because of this, you will decide who will survive. The selection operator will be done based on this fitness, right? So parent will survive or the child will survive based on this fitness, right? So this is the fitness. Let me call this fitness. Few people convert this function value, scale this function value in the range 0 to 1, and then they call it fitness. So let me just right now call this as the function value or the fitness together. I'm going to apply this strategy, DE rand 1 bin. What does it mean? If you remember, I explained you 10 strategies, but now I'm going to explain you, I'm going to apply this strategy, differential evolution, randomly selected target vector. Only one difference vector because I have taken only 5 5 population size, and the binomial operator because I have explained you the binomial operator. So let me start with the mutation operator. The first step is the mutation operator. This formula I already mentioned. Megha Gupta, please mute yourself. Here it should be noted that so trial vector I'm going to generate here in this mutation operator. So first of all, let me select the trial vector and these three vectors, and this I'm going to do for the each parent vector. So let me first select it for the x1. पहला x1 है. The for first x1, this is the parent vector. This is the parent vector I have selected, right? I'm going to do it for x2 also, x3 also, x4, x5 also. For everything, for every parent vector, I will do it. So let me do it for the first parent vector. And the corresponding function value is this. This is your corresponding function value, right? This is your corresponding function value. Now, why I categorically write the function value here again, because this function value will then be compared with its child. Now we actually, the ultimate objective is to generate the child for this parent, right? And for having a child we need a mother, and so let's generate a mother, and the mother's father is this x4. Let's generate the mother with the help of x4, the target vector, which is again randomly selected other than x1, right? This parent x1, right? I'm going to modify this parent, right? So for this parent, the mother should be different from this first parent, right? So from x2, x3, x4, x5, I can choose anybody as a target vector. So I have selected this target vector as x4. It is randomly selected, no calculation, just to keep in mind that it should be different from x1, right? So this is your target vector, right? Now for this formula you need two randomly selected members also for this differential, right? So let us select these two differential vectors for this differential. Let us select these two random vectors as x5 and x3. Again, these are selected randomly, but to keep in mind that they should also be different from the parent and the target. Parent vector and the target vector means all these four, parent vector, target vector, two randomly selected members, all these four should be different, right? The scaling factor 0.5 I already taken. So now let us apply this formula. Let us apply this formula, and here is the formula. This is your first parent vector. So first parent vector's child is u1. Let me call it u1, and let me tell you that the mutation operator is applied component wise. This component wise update, let me tell you, the component wise update is applied to many algorithms, like in particle swarm optimization also. Every dimension is updated separately. Here also every dimension is updated separately. So you have two variables. So first variable will be the child's first variable will be calculated separately, and the second variable will be calculated separately. Why I'm calling it u1? I hope you understand that x1 is the parent. So the surname, Bansal, right? So my son will put the surname, my surname, right? So similarly, the child is putting its surname, so 1, right? Just to make sure that this is the son of the x1, right? So u1, and this is the first dimension. This is the first dimension of first variable. So it is the target vector x4. So for first variable, you will select first variable of the target vector. 0.5 is the scale factor multiplied by x5, these two vectors randomly selected x5 and x3. So they are first dimensions, right? And now you can see here x41. So in this population, you can see here x41 is this, x51 is this, x31 is this, right? So all these values will be written here. All these values are put here, and you calculate this u11. I hope I'm clear to this. The first variable is calculated for the child. Child is generated, but first variable. Similarly, I will do it for the second variable, the same thing, right? So second variable for the same variables will be selected, and this is the second variable. Finally, this is the mother. This is the trial vector, complete trial vector you have calculated. Done. mutation part is done. But before moving forward, we need to take care that the generated mother is actually a human being or not, or it is some maneuver, like, you know, you have created a mother, but this is actually a mother or not, means it is eligible to take part in the crossover or not, means it is within the search space or not, means it is an insan or not, right? So you will check whether it is in the range -5 to 5 or not. Both the variables should be in the range -5 to 5. If they are not in the range -5 to 5, then you will keep them to the corresponding boundary, right? There is a lot of other strategies also. It's a long story about the about keeping the solutions confined in the search space. I'm not going into deep into that, otherwise it's a complete lecture. So but just simple that if it is not in the search space, put them to the corresponding boundary. Or right now, since they are already in the search space, so we will accept this trial vector. Now you have two parents. One is the parent vector and one is the target vector, father, mother. They will take part in the crossover, right? And I already told you, if you remember this formula, if you remember this formula, okay, here this instead of capital J, it is denoted by capital I. So please don't set of crossover point, this set of crossover points. So this child, this offspring child is taking the gene either from the target vector or from the parent vector based on this set I. If that particular index is in this set I, then it is taken from the target vector, otherwise it is taken from the parent vector, right? So let us create, let us generate, let us construct this capital I. So in the binomial crossover, if you remember how this crossover, how this set is generated, first of all, I will take you have two dimensions, 1 and 2. It's a two variable problem, so dimension is 2, 1, 2, 1 and 2. So you will take 1 out of this 1 and 2. You will take first of all any members randomly selected, J asterisk. If you remember, J asterisk you will select randomly. So I will take this 2 out of 1 and 2, randomly selected anything, right? If it is suppose 1 to 5, then I can take anything, suppose 4, right? So 4 will be here then. So this I should start a non-empty set, and for non-empty you will take randomly selected member from 1 to 2, right? So 2 size is there, sorry, 2 dimension is there. So out of those 2, you have selected this randomly in this set of crossover points. Now other crossover points, this set will be increased or not, that will depend upon this binomial crossover. So look here, we will run this loop for all the dimensions, 1 to problem dimension. Fortunately, we have only 2 dimension here, right? 1 and 2. So let us start with the 1. First of all, let us start with the 1, j equal to 1. For this j equal to 1, I will generate a random number between 0 and 1 and will check whether it is less than 0.7 or not, right? If it is less than 0.7, then particular that 1 will be included in this set I, then it will become 1, 2. So let me tell you that I have generated this random number between 0 and 1 at 0.67, and this 0.67 is less than 0.7, and therefore this one will always so be included in this set capital I, and so now this set become 1, 2. Now further I cannot run this loop because for j equal to 2 it is already there and j equal to 3 is not there, only 2 variable problem. So this I is constructed, this set of crossover point is constructed, right? It is now there, I equal to 1, 2. Fortunately or unfortunately, whatever, all the genes are coming from the mother, right? All the genes should not come from the father. If they are coming from the mother, the target vector, then definitely you can expect some change in the solution, some change in the offspring. If it is coming from the parent, then it is a copy of the parent, right? So you cannot take I as empty. You can take I as the complete set of dimensions. That is okay. That is recommended, but not the empty set. So I equal to 1, 2. So now the offspring x1 dash will be, I told you that if this 1 is there in this set of crossover point, then that particular variable will come from the target vector or from the mother. So you can see here, this is your mother or this is your target vector, right? So the first variable will come from here. The second variable will also come from here because that is also in this. So your child will actually the copy of the mother or the target vector. So here is your child or the offspring, and this is actually the copy of the mother. Right now it may be different, it may have some gene from the father also, but for this example by chance it came like this. So now you have the child, you have the father, you have the child. Now the third operator, the selection operator. Selection operator is to be implemented. So for selection operator, you will check the fitness of this offspring or of this child. So let us calculate the fitness of this, and it is found, fitness means put this value in the objective function and you will get this value 19.9417. You know that the parent's fitness is this. You can see, you know that the function is minimization problem is minimization. So this value is better, this value is better than this value. It means your child is better than the parent, better than the father, and therefore the father will die out and the child will survive, right? So this child, the new x1 will this, the new owner of that location of that house is the child. So x1 will be replaced by x1 dash, and this will be your new solution instead of x1. I hope you got my point, how we are modifying the solutions. So this is the way how we have modified the first solution. The same thing we will apply for x2. Now the parent is x2. We will, for x2 we will apply that mutation target vector is this. These are the two randomly selected solutions. This is the trial vector after the mutation operator, then the crossover. You have this new x2. Similarly, you will do it for x3, x4, and yes. Solution. We're happy. Then
Sir, your voice is breaking, sir.
Dr. Jagdish, right now some problem on the network, maybe.
yes. It's more. So just let you know, keep showing me. I mean, my
Still problem is the same. You
uh,
may rejoin. You may rejoin.
I'm not audible. I'm,
Now coming. Now
I
it
think
is
now I'm
coming.
audible. I have switched off my video.
Yes, you
Is it
may
okay?
stop video now. So that.
Yeah.
Yes, yes.
So am I
Now it is
audible
coming.
now?
Yes.
So here, just quickly, give me 5-7 minutes more, and let me just quickly explain you its MATLAB code also. So this code is also explained in 4 parts. The first part is the problem definition. So here again, the same problem is sphere function I have taken. Dimension is 20. So 20 decision variables. Range is -5 to 5, and the var size is just to store the variables. The second part is the DE parameters. Iterations are 100. Population size is 50. Scale parameter is 0.5. Probability of crossover is 0.7. Third step is the initialization. You have two structures for position and the function value, the cost, right? Initialize the cost with the infinite because it's a minimization problem. If it's a maximization, you can start with the minus infinite. Here is the population, complete population. So RepMet function we used for this, and to generate this population, you are generating this unifriend command used for in the range -5 to 5, and these are the number of variables, var size. So population, and then its cost, means function value you are calculating, finding the best solution, right? And then the last step, fourth step, the major step, you will first of all select the parent. So for every population member you are going to do it for this. So for each I, I'm going to take this x pop I dot position as the parent, right? And for this parent, I have to find out the target vector and two randomly selected member, target vector and two randomly selected vector. And therefore from all the population, for all the population members are permitted randomly in this capital A. So from this capital A, I will select target vector, randomly selected vector, two random vectors, A1, A2, A3, right? They are randomly permitted. So you first take first three. So you can choose anyway, right? This, you have to choose three different vectors from the population other than the parent vector, right? And therefore, this is the one way you can take, you can select them in some other way also. And then the mutation operator. So this is the formula for mutation operator. The trial vector is generated here in this formula. U equal to the target vector, pop A. A is the target vector, B and C are the other two vectors. Plus F is the scale factor multiplied by, and look here, this is the component wise, so dot multiplied, right? Component wise, for first dimension it is separate, for second dimension it is separate, third dimension it is separate. These are the two vectors. You just keep them in confinement, means if you make sure that after this it should be within the range, and then the crossover operator, for this you generate some z as zeros, and j naught is selected randomly. J naught is actually j asterisk, so it is selected randomly in the range 1 to numeral of x, means the dimension of the x. This j naught is selected randomly. Now for all other things, 1 to numeral of x means 1 to dimension of x, 1 to 2. For example, in our numerical example, it was 1 to 2. If it is 20 dimension problem, then it is 1 to 20. So j is, if it is, it should be not equal to other than the j naught. You consider based on this probability of crossover, then it is coming from the target vector, otherwise it is coming from the parent vector, and you have a new solution z. Now this new solution z will survive, or the parent will survive based on this selection operator, that the new solution cost, if it is less than the ith solution's cost, then the new solution will become the ith solution, otherwise it will remain the same. And then calculate the best cost. That's all. Update the find and report the best solution. And these are just for the display of the results. And here is the sphere function. Here is the definition of the sphere function: sum of x1 square plus x2 square, dimension wise squares. That's all. This is the so simple code. So means I'm sure that if I'll share with this MATLAB code with you, it will not take more than 10-15 minutes to understand each and everything of this, if you know the MATLAB, of course. 5-7 minutes, 10 minutes, maximum 10 minutes to understand this code, right? So best of luck for the learning of differential evolution further. Let me tell you that here in this lecture, I have Sir, am I audible?
Yes, audible.
I'm audible, sir.
Yes,
Yeah.
yes.
So I am here. I have removed the inertia of understanding differential evolution. Now up to you that how much explore you this algorithm further and read it. After understanding these basics of this algorithm, I'm sure that you will be able to understand the research papers on the differential evolution. You read 2-3 research papers, and definitely I'm very much sure that you will have a new idea further to develop a new algorithm or new improvement in differential evolution. This always happens. And Dr. Krishna Pratap know that this is the way how we improve the algorithms. So
Yes. So if
that's
anybody
all
have
from my
any
side.
question, if
Yes,
anyone
sir,
have
I have
any
one
question,
question.
quickly we can take. Yes, yes.
Sir, can we use this algorithm to multi-objective optimization problems with so many constants,
Yes,
like different
definitely.
constants?
Definitely. There are multi-objective variations of this algorithm. So already multi-objective version of differential evolution is available. You just Google it. You will find the multi-objective differential evolution, very popular. However, this can be applied very efficiently, but still it is not one of the best choice for multi-objective optimization problem. For multi-objective optimization problems, still the genetic algorithm, particularly the NFPA2, is still the best choice, right? It is applied. It is applied to the multi-objective optimization problem, and it can be applied, but still it is not the best choice. It is the one of the top choice for the continuous optimization problem, single variable, one optimization, single optimization.
Okay, sir. So, what are the major drawbacks of this algorithm? What are the major drawbacks?
Good. I'm happy to hear this question. I just avoided this question, but just for the okay, this algorithm is very good question, and I'm really happy to share this. Can others mute? There is a background noise. KP sir, can you please mute? Yeah. Uh, this algorithm has one significant drawback is the fast convergence, less exploration over the exploitation. This algorithm exploits more and explores less. This algorithm has no mechanism if there is a stagnation of this algorithm to a local optima. There is no mechanism of coming out of this. Actually, this algorithm is made for that purpose. Algorithm is quite old, 1995 it was introduced. Now there are many algorithms which has introduced the mechanism to come out of the stagnation. Let me tell you, there is no mechanism in this algorithm. I have explained all this. If the solution is not improving, if all the features are coming from the parent, just imagine if all the features are coming from the parent, or the mother is also very close to the parent, means the target vector is also very similar to the parent vector, then even if the genes are coming from the target vector, they are not much different from the parent vector, right? And then the child will also have almost similar, so the improvements may not be much different. Means there is no occasional jumping from the current situation to the new positions in this algorithm, while in like artificial bee colony algorithm, or the spider monkey optimization algorithm, or the gray wolf optimizer, all these algorithms has the inbuilt mechanism of skipping the true optima. So when you have the requirement that this algorithm, you need the solution quite fast. You need the solution very fast. If you need the solution very fast, and most of the time, if you know that your solution is unimodal, then this algorithm is very good. It is highly recommended algorithm, right? So because there is no problem of exploration. Exploitative algorithm can only work for the unimodal problems. So, but if it is multi-modal, then this algorithm can converge to the local optima also, right? And stagnate, that is called the stagnation problem. So this is the major problem. The advantage of this algorithm is that it has very less number of user parameters. right? User defined parameters are very less, while other algorithms like spider monkey optimization algorithm, gray wolf, or the artificial bee colony, or the biography based optimization, all those algorithms have a lot of parameters to be set by the users. So they have their own drawback. It has its own drawback. So, there is no single algorithm which is the best algorithm. Let me tell you, you have to bear with, and according to the situation, you have to apply. So if you have less time and you are aware of your problem features, you are aware of your problem properties, that it may be unimodal, very high chance that your problem is unimodal, then it is highly recommended algorithm, right? I hope, and
Yes,
also
sir. Yes.
this here the mutation operator is based on these differentials. So once the population is converged, is differentials. So everything is dependent upon x1 minus x2. So if this difference is less, there is no chance of improvement, right? The improvement is less. If the difference is zero, tending to zero, the change is tending to zero. Ultimately, your solution will become stagnant, right? So that's the major drawback. And many people have introduced the new mechanisms to come out of the stagnation. So other kind of extra mutation people have introduced in this algorithm, right? And people have taken the multi-population based differential evolution also. This algorithm also deteriorates. The performance of this algorithm also deteriorates if your problem dimension increases. You cannot apply very efficiently this algorithm for high dimensional problem, 500 variable problem you are dealing. Then this algorithm is less efficient as compared to other algorithms, right? Other similar category algorithms. So that's the major differences, major drawbacks. Okay, any other question?
Okay. One question Dr. Kumod is asking that how to use this one in the deep learning parameters.
Yes,
Yeah.
I think you know
What I
that
can
these
suggest, Dr.
questions can
Kumod, you may put this differential evolution with all ADAM and ADA grade like techniques which are generally used in the deep learning model. But what Dr. Bansal suggested that as the parameters increase, the efficiency of differential evolution and evolutionary algorithms may decrease. So what I can suggest, and still is the further future research also very less works in that direction, but you can put this differential evolution with ADA grade or ADAM. Those are the most popular algorithm right now in the deep learning, with which may be helpful to improve the accuracy in the fast way. That's where you can look up to hybrid these two techniques. So with this, I would like to thank Dr. Jagdish for introducing differential evolution, and I hope participants have enjoyed this talk. And the whole evolutionary algorithm, what I can conclude that as the always parents guides to child to find out the path in the life, to explore the new thing. The same kind of inspiration you may follow, and you can develop such a evolutionary algorithms, maybe DE or maybe genetic algorithms, or you may see other philosophy of the nature, and you can develop, you can see the many in literature different kind of algorithms which are working very fine. So with this, I would like to thank Dr. Jagdish again for sparing time and giving such a nice talk on this. He's working in this, especially he has developed this spider monkey algorithm, which is very, very successful. If I'm not wrong, Dr. Jagdish, that algorithm is very successful.
Yes, sir. Nowadays it is getting popular throughout the world. People are working almost all in all the regions of the world. People have worked on this algorithm. They have applied or modified that algorithm. So now it is an established algorithm.
Yes, so he has very good work in that area. So I'm hopeful that definitely you all have enjoyed. Thank you, Dr. Jagdish, for giving valuable time.
Hello, sir.
Thank you.
Yes, someone is, yes.
Sir, can I get your Jagdish sir? Can I get your mail ID? So I am from Sir IIT Roorkee also. So I want to talk to contact you for further, some doubts if arises.
It is very simple. I have written in the chat. You may all copy.
Yes.
No worries. And I'm open, and you can search my name. You will find my web page there. I uploaded the video lecture on this differential evolution also I uploaded other materials also of these kind of algorithms. So you can download at any time, even if it is not necessary to share. I have already uploaded all the things. So no worries about the material. Even if you want particulars of material, you can always write to me. And most of the time, the laptop is with me, but just for 2-3 days further, also I'm busy somewhere for my family regions. And after that, I will be full time available. So my response may be delayed for next 2-3 days.
Thank you. Yes,
Thank
thank
you,
you,
sir.
Dr. Jagdish, again. And again, all the participants, we will meet again at sharp 11:45. It's the 15 minutes break for tea. Even though as an organizer, I'm not serving the tea because it's online mode, but you may take your own tea and meet sharp after 15 minutes. Thank you.
उधार रहा
Thank you,
सर,
Jagdish.
उधार रहा सर, इलाहाबाद के लिए उधार
Yes,
रहा.
yes. Anytime.
Okay.
Otherwise, I would come in Delhi or you come in Allahabad.
Yes, yes.
Thank
Okay,
you.
bye.
Thank you.
Bye. Bye.
Thank you. Bye.